let's look at one example. This Fermi function is just a probability, but still we need to find out what is the real occupancy of the electron. So let's assume here this is a different energy level. And each box has 10 available states. 10 available states for the electron. This is a different energy level, but each level it can hold at most 10 electrons. Then we need to consider the probability of those electrons according to the Fermi function, where you have EF somewhere here. Then the question is, what is the actual number of electrons in those boxes? Any idea? Those are the available states, and this is the probability to fill those states. Then if you use those two multiply together, you will get the actual number of electrons in each box. So here, this is the electron occupancy. Because here this is available states. This is the available states. And this is the probability. So here at the bottom, so the probability is 1. So you have 10 states, and all of them are occupied. So you get 10. And then here you get another 10, and this roughly is 10. But starting from here, the probability drop. So probably you get 6, and then here you get maybe 3, and at the very top you have a little bit probability, maybe you get 1. So this is why we use this probability to find out the actual electron occupancy. Any questions here?
So this is as the energy is decreasing, right?
Yeah, so the pointing up is the energy up. Yeah. Let's look at another example. So if the states, the number of available states change as a function of energy, like this, the lower energy has less available states, and higher energy has higher available states. Then how does this actual electron occupancy look like? So still, you need to think about the Fermi function with EF somewhere here. And then you need to multiply this one with this one. So at the bottom, you have 3 states. Then all of them occupy 3. And then this 7 becomes 7, 13 becomes 13. But starting from here, this 18 probably you only get 10. And then when you go up, although you have more available states, but the probability becomes smaller. So the actual number of electrons gets smaller. So eventually you will get this kind of distribution of the electron. Okay, so I can have another analogy to help you understand this. For the left one, this available states, you can think that in this classroom we have many seats, right? And then you guys are what? electrons, right? So you need to sit in those seats. So then maybe let's say towards here, you have lower, let's say, energy. To the back, maybe higher energy level, right? So maybe in the first row, we only have 2 seats here. That's the bottom. The first row, here we only have 2 seats. And then here we get more seats, and then more and more seats. And then, of course, right now your distribution is unlike the Fermi function. If it's like Fermi function, most of you should sit in front, right? But you can think this way, right? The available states are the seats, and you guys are electrons, and then you need to fill in those seats according to some rule, and the rule is the Fermi function. Any questions here? All right. So why are we interested in these examples? Those examples, because in the actual silicon, we do have this kind of density of states with this kind of shape. So this is the actual silicon. This is the energy, and then this is the available states. This shape is similar, like something like this. This is kind of triangle, but in actual, is in the silicon in reality, it's something like this. So this is the EC, the conduction band edge, and above the conduction band edge, we will have the available states, or the empty states for the electrons to occupy. And then we are going to use this density of states to describe how dense those states are. And if you consider a small delta, let's say dE, a small step of the energy level, then here this region means the number of states that the electrons can occupy. And then below the EC, this density of states is 0. Why is that? Because that's band gap, right? So you don't have states for electrons. But above the band gap, starting from EC, the higher the energy, the more available states for electron. Similarly for the holes, because holes are in the valence band. Here, remember, once you kick out an electron, you get a hole, the vacancy of electron. So the hole will have similar density of states, but it's in the valence band below the EV. So this is similar for the hole. Any questions here? So this is the distribution of the seats, basically, in the classroom. And this GCE describes how dense are those seats. Then the question is, how do we get the real, let's say, number of electrons in the conduction band? What is the density of the electron in the conduction band? The same practice, right, as we did in the toy model earlier. So this is the density of states, similar as here. This is like density of states. Now we have this shape. And then Fermi level and Fermi function. So because Fermi level is in the band gap, so it's somewhere below the EC. And then we have this kind of Fermi function. Of course, depending on the temperature, you get a different slope here. So then, to get the actual electron density, you need to use density of states multiplied by the probability. Then you get this. It's something like this. Right. So it will start from the EC. Because below EC there's no states available for electron. And then above this EC, then you will first increase because you have more states available. But later, because the probability will go down, so then it will go down. So you have a distribution of electron with different kinds of energy levels in this kind of distribution. Any questions? This is like the toy model before. And mathematically, you can derive this. So the density of states essentially is let's say the density of electron essentially is the density of states multiplied by the Fermi probability. Let's say at this dE level, there's a small dE here. You get some dE level. You get something here. But you have to integrate this. Because you start from the EC up to infinity. So this is a mathematical way to derive the electron density in silicon. And it's a very tedious derivation, I'll skip that. But eventually, people use the following formula to get the electron density, like this. So here, electron density equals to NC times exponential function EF minus EC over KT. So here NC is called the effective density of states in the conduction band. So conceptually, is you think that all the electron is occupied at the EC level, and then the EC level will have effective density of states NC. So let's squeeze this whole distribution into a single level, and in that level, we'll assume the available states, number of available states is NC. So that's why it's called effective density of states. And this is a constant for silicon. And it says it's 2.8 times 10 to power 19 per centimeter cube here. So you can also, let's say, we can use an easier way to remember this equation. So what matters here is this distance between EF and EC. So here is EC and here is EF. So we care about this difference, which is delta E. So you can always assume N equals to NC E, and then this delta E divided by KT. The distance between EC and EF. And remember, this delta E is always negative, smaller than 0. That means N is always smaller than NC. Because exponential, you know, if you have a negative term here, then this exponential is less than 1. So N is smaller than NC. Any questions here? So this Nc is a physical constant. You cannot tune that, okay? And Kt depends on your temperature. So if you want to change the density N, the electron density N, that means you have to move the EF up and down in the band gap. Alright, so this is for electron density in silicon. Similarly, you can have the hole density in silicon. So the same approach, you have the density of states for holes, which is starting from the EV, and then the occupancy, the probability of a hole is 1 minus Fermi function. Why is that? Because you know electron and hole are complementary, right? So you have a vacancy of the electron, that means you have a hole. So then if that state is occupied by electron, then the probability of occupying hole will be 1 minus the Fermi function. So then you just reverse the function. If you compare those two, this is the Fermi function, and 1 minus that will be just something like this. And again, you can do the integration. This one multiplied by this one, and then you do the integration, you will get the whole distribution here. And again, you can squeeze this into a single level. And you think this single level has an effective density of states NV. Then you can get the whole density, P equals to NV times EV minus EF over KT. And similarly, this you can think this is the distance delta E over KT. The delta E is the distance between EV and the EF. And again, this delta E is always negative, so you will always get P smaller than NV. And for silicon, NV is 1.04 times 10 to the power 19. Any questions here?